So, we are studying basically the rotation of a molecule. So, we have chosen diatomic molecule, linear molecule, and we have taken model, that rigid rotator model. So, when this molecule will rotate, there will not be change of the bond length. Okay. So, considering this model, so we have calculated the energy in terms of wave number Ej equal to I think B j plus 1. Okay. J is the rotational quantum number, J is rotational quantum number, okay, and B is the rotational constant. So, B it B equal to I think h by 8 pi square I think IC, okay, and I is moment of inertia, is mu r0 square, right. So, that we have seen, and we have seen also that if I calculate nu j bar, so that is basically this transition from one rotational state to the another rotational state. So, transition from between this j plus 1 to j. Okay. So, between these two energy levels, if this transition is there, so we will get the radiation, that is in microwave range, and that radiation wavelength or wave number will be what we got, that is I think 2b j plus 1, yes. So, that is what we got, and using the selection rule del j equal to plus minus 1, we have seen that this will get spectral lines, they are equispaced. So, this energy of the spectral lines, it will be, this is 2b, 4b, 6b, 8b, 10b, right. So, these the spectra we will see from linear molecules if it is rigid rotator, if it is rigid enough so that their bond length is not changing during the rotation. Okay. So, now what is the use of the spectra? What is the use of the spectra? What is the use of the study? So, that is the basically microwave spectroscopy. From microwave spectroscopy, one can get some information. So, one example I will give you. So, this Gilia metal basically, Gilia metal. So, he measured this wave number of this first spectral lines for which molecule? Cobalt monoxide molecule. Okay. And he measured this. So, spectroscopically, so that is the spectroscopy. Spectroscopically, I can measure the wave number of wavelength or energy of these spectral lines. So, Gilia metal, he measured the first line, means transition from 0 to 1 in the rotational spectra of cobalt monoxide, and he found the value of this spectral lines is 3.842 centimeter inverse. Okay. So, from theory we have seen this. So, that is nothing but is equal to 2b. So we can write 2b equal to 3.842 centimeter inverse. So b equal to 1.921 centimeter inverse. Now b equal to this. So b, what is b? So b, as I have written, b equal to this. So from here I can write I equal to h by 8 pi square bc. That's what I have written. I equal to h by 8 pi square bc. Okay. So c, so that is 1 by b. So I have written separate. I have written separately this 1 by b, because b value I know from experiment. So if I put b value and other are constant, you see c, this velocity of light, pi and h, these are constants. If I put this value of constant, so I, moment of inertia, I will get this value 14.569 into 10 to the power minus 47 kg meter square. Okay. So I was able to calculate this moment of inertia. So moment of inertia I equal to mu r0 square. Okay. So mu equal to m1 m2 by m1 plus m2. So m1 is, if it is mass of carbon, then m2 is mass of oxygen. Okay. So mass of carbon. So so this is the mass of carbon. So this, I think, yeah, mass number is 12 for carbon, and this for oxygen it is 16. So 12, and then this is the mass of hydrogen, no, 1.67 into 10 to the minus 27. If you multiply it with this, then you will get the mass of this, weight of this basically. This mass in terms of kg you will get for carbon and for oxygen. So now mu you can find out from this, mu equal to m1 m2 by m1 plus m2. So mu is this 11.383 into 10 to the minus 27 kg. So now mu you know, so r0 you can find, mu you know, and I also you know, this value is available. So r0 will be square root of I by mu. Okay. So if you put these two value, so it is coming 1.131 angstrom, and r0 is nothing but bond length, of cobalt monoxide. So this is very nice experiment. Okay. So just from rotational spectroscopy, one can, or this also called microwave spectroscopy, one can measure the energy of the spectral lines. So first spectral lines or second, third, fourth. Okay. But first one is the intense one, other one is difficult to see, that I will discuss. So why he measured the first one, so that I will discuss. So intensity of all these spectral lines are not same. So only this first one is very bright, and other one is with higher orders. So second, third, fourth, they are very weak. Okay. So but measuring the first one is, if you find out, so then we have seen that using the theory, rigid rotator model. Okay. So using whatever from this theory, whatever the expression we got of energy or the spectral lines. So if we equate this theoretical energy of spectral lines with the calculated or experimental energy of the spectral line, then from there one can calculate or find out the bond length of molecule. Okay. So this is the nice way to measure the bond length of molecule. Okay. So this one nice example of application of this, for this studying of the rotational spectroscopy of molecules. So next I can I basically, as I mentioned, that all molecules, they are all spectral lines, intensity of spectral lines, okay, first line, second, third, fourth line, they are not, intensity are not same. So, why they are not same, that we want to find out. So, before that we should know this, there is a degeneracy of the states. So, what you got? We got this different energy level of the rotator, rigid rotator, or of a molecule, rotating molecule. Okay. So, defined energy level means they have defined. So, these energy levels are allowed, means these are the energy allowed for the rotating molecules. Okay. So, but it is in which state? It is in which state? It can be in one of them. So, there are many states, energy levels. So, each energy levels means if the energy of the rotating molecule, if it can be one of them. Okay. So, then we tell if it is at the lowest energy state, J equal to 0, then we tell this molecule is in ground state. Okay. If it is in J equal to 1, so this is a first excited state, second excited state, third excited state. So, these are in rotational excited state. This rotational energy spectra is like this, and then this molecule, due to its rotation, it can be in one of these states. Okay. Now, each of the states, whether it is non-degenerate or degenerate. So, remember this, in case of hydrogen atom we have seen there, for n equal to 1, then L equal to 0 to n minus 1. Okay. Now, for each L again, about a fixed direction. So, there is a quantum number. So, that is m or ml we tell, right, or m, whatever. So, how many states are possible? That is basically the space quantization with respect to this fixed direction. So, how many this allowed value? So, that is basically minus ml to plus ml. So, total this quantum number is basically 12 plus 1. So, then we tell if energy depends on n and L, okay, but it does not depends on ml. So, then we tell this has 2L plus 1 times degeneracy. Okay. So, that means 2L plus 1 number of states having the same energy. So, that is the degeneracy. So, here as I told that this rotating whatever, this we are seeing that is equivalent to the angular motion, angular momentum. Okay. So, J whatever we have considered, this is equivalent to L basically. Okay. So, due to this rotation, so this energy there are different energy levels, and different energy levels is based on basically different value of J, and there is a degeneracy of each level depending on the value of J. So, what is the number of degeneracy? So, it is basically as I mentioned. So, it is the similar to L. So, for L, how many number of degeneracy we have seen? That is 2L plus 1, 2L plus 1. So, here also in this case degeneracy 2J plus 1. So, 2L plus 1, so 2J plus 1. Okay. So, yeah, here I have mentioned this for rotator, its energy E equal to half mv square, kinetic energy half mv square. Okay. Half mv square. So, m is replaced by I moment of inertia, and its v is replaced by omega, angular velocity. So E equal to half I omega square and P equal to mv. So here I omega. Okay. So this P, one can, from here one can write P equal to square root of 2 E by I. Okay. So and this P is basically in this case here angular momentum P. I have, it is not linear momentum, although I have written P, but it is angular momentum. So P angular momentum, it's the eigenvalue is basically square root of j plus 1 h cross. So L h cross. So in case of quantum mechanics, L is replaced by square root of L plus 1 h cross. So here this j square root of j plus 1. Okay. So that's why, so that's energy. Okay. E p squared by 2m, h cross squared by p squared by 2m. Okay. So in case of linear motion, so here this it is so one can write p squared by 2m. So p squared by 2m means p squared by 2i. Okay. So p is I h cross minus I h cross del kind of things is there. Okay. So from here also energy of this rotator, one can write the h cross squared by 2i j plus 1. Okay. So for just simple way also one can tell, and so it has degeneracy. Each energy levels have degeneracy, and that degeneracy is basically 2j plus 1. Okay. So now what is the meaning of degeneracy? Means I have energy levels. Okay. So each energy levels means state of the, this is the state of the molecules, rotating molecules. Okay. Energy state of the rotating molecules. Okay. Now here energy level and the states, there is a difference in one energy level. So there may be more than one state. Okay. When we tell in terms of state, so that basically state of, so it can be one of the degenerate state having the same energy. So having the same energy, it may have more than one state. Okay. So that means here it's not one state, it is not although energy, this energy are same, but it has many states, few number of states, more than one state. Okay. So that means at that energy molecule have probability to stay that should be proportional to the degeneracy of the energy level as well as energy of this level. So that's why if more, so this one can think other way. You see, I have taken say HCl molecule. Okay. So 100 number of HCl molecules. Okay. So each molecule have their own have their same energy states configuration, but all molecules are not staying at a particular energy states. They can have in different states, because different states of different energy levels are there. Each energy levels again has degeneracy. Now if I have 100 molecules, now these 100 molecules where will stay? What is the probability to stay at j equal to 0, at j equal to 1, at j equal to 2? Okay. In which state they can stay? Okay. So that should be the proportional of the number of states at a particular energy, that is 2j plus 1. This population of the molecules means out of 100 how many will be there, that is called population of this molecule. Or I have say N0, whatever 100 I told, if I take that is N0, okay. Out of N0 molecules, out of 100 molecules, so that is N0, how many molecule will stay in J state. So Nj, that is the number of molecule will stay at jth state, okay, jth energy level. So that is proportional. That is proportional to the basically that is called population. How many will be there? So that will be proportional to j plus 1, no 2j plus 1. That is the degeneracy, proportional to the degeneracy, as well as it will be proportional to the Boltzmann factor. All the time this Boltzmann factor we use. So if this system is at a particular temperature, okay. So then what is the distribution? So that is the Boltzmann distribution. So what is the Boltzmann factor? So e to the power minus E energy by kT. So so this will connect with the temperature of the system and energy of the system, okay. So e to the power minus E j, in our case the energy of jth level is E j by kT, okay. So these are the here it is, it will tell you the population of the molecules, okay, at a particular energy level. So one can show that at yes. So so if I plot this population, if I plot, I think I can plot here. If I plot this population, I think I can show also here this yes, I can show here. So intensity, then that the intensity of spectra will depend on the basically population of the rotating molecules in a in different energy levels, okay. So intensity of spectral line depends on the probability of transition between various energy levels. That is true, okay. So two factors we have to consider. One is population of the levels, okay, and another degeneracy of the level, okay. So that's why Nj this is basically Boltzmann factor Ej. So I have written here in terms of expression. So B j plus 1, now it was in wave number, so that's why you have to multiply with Hc, then it will be energy. So B Hc j plus 1 by kT, okay. Now total population or relative population, actually it's a proportional of both factor. So this is the basically Nj equal to, so here if I take this is as a Nj, this Boltzmann factor, so then degeneracy into this Boltzmann factor Nj dash. So that's finally we are writing Nj. So Nj equal to this 2j plus 1 Nj dash, that Boltzmann factor, and equal to N0 2j plus 1 e to the minus Ej by kT. So that's what I have shown. So if I plot, so this Boltzmann factor is varies like this, with j value it will varies like this. So it depends on B. So we have considered B equal to 5 and B equal to 10. So if higher the B, so exponential term it will be fast, it will decay faster. So this will be the variation of Boltzmann factors. So now we have exponential term as well as the linear term 2j plus 1. So how to plot, you know, I have shown in case of hydrogen atom. So this term is basically Nj, it is basically varies like this. So it will have maxima, you know, at a particular j value it will have the maxima, and it will depend on temperature, of course. So at which value one can get maximum, that you can find out. So that is the standard procedure, dnj by dj equal to 0 gives the value of j. square root of kt by 2hcb minus 1. So, just differentiate it with respect to j equal to 0. So, then you will find out the j value where you will get the maximum population. So, j value, so maximum population will get at j equal to square root of kt by 2. So, it depends, maximum this population depends on temperature as well as depends on B, okay, others are constant. So, so this one can find out easily. So, but just if you take one B value, if you take one B value, B equal to say 2 centimeter inverse, and at room temperature, what is the what is the population at j equal to 1. So, j equal to 1. So, ratio you see n1 by n0, n0 is basically at temperature 0, at 0 temperature. So, whatever the all molecules will be at rotating molecules will be at j equal to 0 energy level. So, now yes, now basically at j equal to 1, what is the population? So, n1 by n0, it will come, if you take this value, this will come 0.98. Okay. So, 0.98 means, okay. So, n1, so there most of the 98% molecule out of 100, 98 molecules will be at j equal to between these two level, you know, j equal to. So, if initial is initial this n0, so for j equal to 1 at n1, j equal to 1 n1. So, at n1 level 98 molecules out of 198 molecules will be at j equal to 1. So, how many numbers will be at j equal to 2? How many numbers will be at j equal to 3, etc. So, you will see this, it will reduce drastically. Okay. So, most of the molecules will be at the lower level. Okay. So, that is why transition we are considering only from so here transition del j equal to plus minus 1, it is allowing from j equal to 0 to j equal to 1, or j equal to 1 to j equal to 2, j equal to 2 to j equal to 3. Okay. So, I think there is a here just slightly I think j equal to 1 I have taken. So, it should be the, so then j value one can choose j equal to 1, 2, 3, 4 that way. So, that is the lowest energy level. So, in lowest energy level 98% molecules will be there and 2% will be at the rest of the j equal to 2, 3, 4, 5. So, from transition from j equal to 2 to j equal to 3. Okay. So, molecule in j equal to 2 is only 1% or less than 1%. Okay. So, even if it is 2% and j equal to 1, it is 98%. So, j equal to 1 to 2. So, whatever the intensity I will get, if it is 90% this population, so I will get 90% this say intensity. So, then 2 to 3 the 2% population. So, I will get the intensity compared to this first one, it is just 2% of that first one. Okay. So, that is why I told this first line only will have the highest intensity, and this next onwards this intensity drastically reduced. So, that that is why we get the intensity, bright intensity only for first line in case of rigid rotator. Okay. Model, and yeah, measuring this first spectral lines, one can predict the wavelength this bond length of the molecule. So, that is why Gilliam, as I showed you, this et al. They did this experiment of cobalt monoxide and they measure only the first one. The reason is that this first one is very bright and that is easy to measure. Okay. So, I will stop here. I will continue next class. Thank you.